Very good. So thank you for coming. Thank you so much for coming to this set of the in-person event. So before starting, I would like to thank the founding that we have. One is Cristina Toninelli, and the other one is CNRS, the Polytechnique. Tell me if I'm correct. And so today we have Cristina Toninelli, who she's going to tell us about bootstrap percolation and kinetically constrained models. And please, the stage is yours.
Thanks. Okay, thanks to all of you, to all the organizers, for the invitation, for making me feel young with this invitation. So I'm going to present today a joint works which has been an ongoing project with Fabio Martinelli in the last 5 years, and then main key contributions were given by Ivailo Artaschi and Omar Esche, my 2 former PhD students, and we also collaborated with Rob Morris. So Fabio is in Rome, Lori is now in Strasbourg, Ivailo is postdoc in Vienna, and Rob Morris is at IMPA in Brazil, where he was also before. Okay, so I'm going to talk about this seed seminar is the junction of mathematics and physics, and this, I suppose today's session is on math, but the subject is at the interface of mathematics and physics. In fact, I'm going to present results on kinetically constrained models, and these are a class of interacting particle systems, so Markov processes on discrete lattices, so with the Markovian dynamics, which have been introduced by physicists in the 80s. And the aim of the physicists, and they have been studying them in the last 40 years by means of numerical simulations, heuristic arguments, etc. And in the last 15 years, they have been very much studied also in probability. So why did the physicists introduce these models? It's because they wanted to have a toy model is enough to be analyzed and meaningful enough in order to reproduce a physical phenomenon, to reproduce a phenomenon which is still far from understood, which is the transitions that occurs when you take a liquid and you cool its you cool it very rapidly, so you decrease its temperature so fast that you don't have time to create a crystal ordered structure in the liquid. So the liquid freezes in a state which is disordered and amorphous, which you know all very well, the glasses. So we have been manufacturing glasses in thousands of years, but still this phenomenon is far from understood. Not only a theory, but even from the experimental point of view, there much is going on. So, okay, so these models, which I will call KCM for short, that's their acronym, have been introduced to analyze this phenomenon. Okay, so let's, oops, yes. So let me start by introducing the class of models. Sorry, at the very beginning, the definition will seem a little bit abstract. In the next slide, there will be examples, and all these abstract geometric things will be clearer. Okay, so they are models, as I said, on discrete lattices. So for today, we will be just on the Euclidean lattice. Think about Z2, say 2 dimensions. So, and on each side of the lattice, either it is empty or it is occupied by one particle. So it's a on each side there is a 2-state space. And in my drawings, occupied sides will be filled black dots. And the empty sides, I'm sorry, I just noticed before that sometimes they are just empty, and other times there is a white dot. The white dot means empty in my drawings. Okay, so how is it this? Okay, this is the space of configurations, and how does the dynamics evolve? I told you that it is a Markov process, so at continuous time. And how is it defined? So first of all, in order to define the model, I told you it's a class of models, so there will be some parameters, which will be like a parameter which corresponds to essentially the temperature, but there will be also a class which is defined by some, which will on which you can, there will be some things that you can vary on the rates of these models to navigate on the whole class. Okay, so first of all, you have to define a model to fix a density parameter. It's this parameter which I call Q. It's a parameter in the interval 0, 1. And this Q, I tell you it from the very beginning, it's the equilibrium density of empty sites. So it's the probability that the site is empty at equilibrium. And then the other thing that you have to choose, which here is where it seems a little bit abstract, is an update family. So what is an update family? The update family, which it's what I call with this slanted U, is a finite collection of local neighborhoods of the origin, which means that it's a collection of sets, U1, UM, M is fixed and finite, and each UI is a subset of the lattice, and the only requirement is that it is of finite range, so it's not infinite, and it should not contain the origin. Okay, so once you have chosen such a set, then as you want, then you have defined the kinetically constrained model, and the dynamics is defined as follows. So first of all, I will say that when I have a configuration, so I pick a configuration eta, so I pick a certain choice of empty and filled sites. And then for each site, depending on the choice of your constraints, I can decide whether the constraint is satisfied or not at that site for the configuration I'm looking at. And to decide that, if I'm looking at a site, if I'm looking, I have my lattice, and I'm looking at the site X here. In order to decide whether the constraint is satisfied or not, what I do, I take this finite collection of local neighborhoods of the origin, examples just in the next slide. I translate them around this site, so they do not contain the origin. So I will translate them here, so they won't contain this site X, they will be around here. And the constraint is satisfied if at least one of these sets is completely empty in the chosen configuration. Okay. And then the dynamics, so we come to the dynamics, and then I give examples of the constraints, is as follows, very simple. On each side of the lattice, I have an exponential clock of mean time 1. Clocks on different sites are independent. It's the standard definition for interacting particle systems. And then when the clock rings on a given site, the first clock that rings, I check whether that site has the constraint which is satisfied. If this constraint is not satisfied, I do nothing. So I go to the next clock ring. If the constraint is satisfied, then I update the configuration on that site by setting it to empty with probability Q. Q is my parameter. Hadn't played a role for them, plays a role here. So I put it empty with probability Q and occupied with the complementary probability 1 minus Q. So examples immediately. So then the first example, one of the models that has been more studied is what is called the two-neighbor KCM, or also called, from the name of the inventors, the Fredriksson and Andersen two-spin facilitated models. Fredriksson and Andersen, one is a chemist and the other one is a physicist. So they introduced this model, and in this case, the choice of U, these sets of a collection of finite subsets that do not contain their origin, contains all the possible. So if this is the origin, so now here I have the site origin. U is composed, I look at is composed by all sets which contain exactly 2 nearest neighbors of the origin. So the nearest neighbors of the origin on Z2 are these 4 sites. And then U are all the possible sets. So U1 could be this one, composed by these 2 sides. Then U2 with another color is composed by these 2 sides, etc. Till I have all the choices of possible sets containing exactly 2 neighbors. So here, what does it mean? If I rephrase all the construction, it means that the only sites that have this constraint satisfied are those that have at least 2 empty neighbors. Because in order to have at least one, I want at least one of these UI to be completely empty, which is the same as saying, in this case, at least 2 empty neighbors. And if So essentially what happens during the dynamics is that at rate 1, all the sites that have the constraint satisfied are updated. And they are updated to empty with probability Q and to occupied with probability 1 minus Q. Perhaps they are updated to the same configuration they had before. Once I decide that I update, I flip a coin with probability Q, I put it to empty, 1 minus Q occupied, independently of what there was before on that side. Other, say, popular in the sense that they have been much studied in physics, choices of models, but it's not just to make a zoology, it's because we will see that all these choices that I'm giving here will belong to different universality classes. They will have a quantitatively different behavior. So the first natural choice is to consider the same, I told you that this model is called FA from the name of the inventors, 2F. Okay, the acronym is FA2F, Fredriksson-Anderson 2, because it's the minimal number of nearest neighbors that are empty. F stands for facilitation. They are those that facilitate the motion. And then it's natural to think that in 2-dimension, one could consider also the case in which I require at least 1 empty neighbor, or at least 3, or at least 4. 2 of these models are trivial in a sense, we will see it later. One is not trivial, it has a different behavior than the 2-spin facilitated. Another possible choice in 2-dimension is the East model. In this case, so the East model is the case in which it's a case in which the origin sits here in order to update the origin, and then the same if I translate to know the other rules. I need to have either the site to the right or the site below empty, one of the two, because I have two update two sets in U. One contains this site and the other contains this one. So it is enough to have one of these two empty. Then there is a tougher model which requires a harder constraint. It's the one which is called Northeast, in which both of them should be empty. So in this case, the update family contains a single set which contains these two sites. Both of them should be empty, otherwise the constraint is not satisfied. And the last model that I want to mention is one which has these three update sets, which corresponds to saying that I want at least 2 empty nearest neighbors, but I don't care about the site on the right. I just look for them up, below, and to the left of my site. Okay, this is called Duarte model from the yes.
The universality of these different these 4 models, or actually 5 models, all different? Or?
Yes, no, that's a yeah. For all these, they are different. Okay, so some properties which are common to all these models with the kinetic constraints defined as I defined. So the first one is a very nice property, even too nice. It seems that we look at it, it seems that the models are trivial. So the first property is that the dynamics is defined in such a way that we have a very simple equilibrium measure, which is the measure which is product and which gives probability Q to empty sites and 1 minus Q to occupied sites. So it's like we are having a Gibbs measure, which is with a trivial non-interacting Hamiltonian here. It's the same thing. So why? But you can check immediately that the way I define the rates, they satisfy detailed balance with respect to this measure. So the true reason is that the constraint doesn't look at the site which I'm going to update. So that was the key important thing, saying that the constraint, these sets which constitute the family U, should not contain the origin. So when I want to update the origin, I don't have to look at the configuration at the origin. So the configuration later on, it's not related to what I had at that moment. So when the constraint is satisfied at the origin, I update to empty with probability Q. And after I have made this transition, which I've made this update, the constraint is again satisfied because I changed just the origin. If the constraint was satisfied before, it's satisfied again. And with probability 1 minus Q, I can make the reverse move. Suppose I was occupied at the beginning. So with rate Q and 1 minus Q, I do the independently of what was the constraint. So for those that know more complicated models like the stochastic Ising model, which is the more commonly studied interacting particle system with birth and death moves. It's just a Glauber dynamics. So it's a dynamics for those that are familiar with the interacting particle system, which is a dynamics of birth and death. And you could think, okay, but this model is much more trivial than the stochastic Ising model, which has a equilibrium measure, which is which has an interesting structure with interactions. So that's true. But there is a second property in which in contrast, this is much simpler for the Ising model than the dynamical Ising model than for these models, is that here the dynamics is not attractive. So for those that are familiar with the interactive particle system, I'm referring to the usual notion of attractiveness. For those who are not, and I'm saying that the Ising model, the stochastic Ising model, if you don't know about it, you won't need to understand it. It's attractive, and our models are not. But it's simple to understand the meaning of this, at least in roughly the meaning of this concept of attractivity. A stochastic dynamics is attractive when of this type of dynamics in which configuration are of the form 0, 1, when it's possible to define a partial order among configuration where the order is such is a pointwise order. So a configuration is bigger than the other if for each site the occupation variable of the bigger one is bigger than the one of the smaller one. Okay. And this is just a notion of partial order. And the dynamics is attractive if it's possible to define a coupling so that I can define an evolution which has the right evolution. I have two initial configurations. I can make my interactive particle system evolve from the two. And I can, if the dynamics is attractive, I can couple the two evolution in order that this order is preserved at a later time. So this is possible for the Ising model, and it's not the case here. And the reason is that, so it's quite intuitive to understand why it's not the case, because the point is that if I have two configurations, one containing more empty sites than the other, so one is below the other, it's certainly not true that this can be conserved, this property, because having more empty sites means that more sites have the constraint satisfied, okay? And potentially this means that there are some empty sites which are able to move in this smaller configuration. They can be updated to occupied. I cannot prevent that, so I cannot preserve this order. So yes.
How is it preserved in the Ising?
In Ising is preserved because you have the interaction favors there is an order, because if you have, okay, usually it's defined in terms of plus and minuses, but if you have more pluses, you are more favored to put more pluses. And you have more minuses, you are more favored to put more minuses. While here there is not this, so there are always the empty sites that facilitate motion, but once they facilitate, they don't put a drift into putting new empty sites.
Is it a statement about some kind of renormalization, like if you have more pluses in Ising and then you do some block transformation, you're gonna get to colder and colder?
Not really, but it's no, yeah, I mean, not, I wouldn't see it in that way. But what it's but there is one thing that you could think about, which follows from this attractiveness for Ising model, is that, for example, you can do. Okay, mathematically, what you can do is some what is called the censoring arguments. And in practice, what it means is that for the Ising model, the point is that if you are interested in what happens on your model in a certain region, you are in a window, you are looking around the origin, and you want to know something. In practice, there is something which is very handful, is the fact that thanks to this order that is preserved, if you want to look at something in a certain region, you can freeze around your boundary to the worst and to the better case. You have two extremal cases, and then you can, in the case that locally you don't see the influence of the extremal cases, for example, that everything is squeezed in the same behavior, then you know that also that's the behavior of the two dynamics. While here, you cannot do this type of freezing. Okay. Okay, so I had written here a sentence just to say that the point non-attractiveness in a sense just means that if I inject more vacancy, that can have an unpredictable consequence. It can help filling more sites, so I cannot use this type of arguments. Another observation, which is will be very important, is that for these dynamics, there exist configurations that are blocked, forever blocked under the dynamics, which are frozen. For example, consider these two neighbor rule, the first one that I gave, the one in which I need two empty sites in order to update. And let's consider the configuration on the left. Okay, suppose it's infinite and you have just these empty sites. Now this configuration is certainly forever blocked under the dynamics because each of the sites has the constraint which is not satisfied. Or trivially also the completely filled configuration. The filled one is frozen for any configuration. So in particular, this immediately tells you that the product measure is not the unique invariant measure. It's not a unique equilibrium measure. If I start from a distribution which is concentrated on a blocked configuration in particular, I will always stay there. So this one is particular because it's reversible. It's the more natural one in which we are interested, but there are other invariant measures. And I wanted also to, it's important to notice also that there exist also configurations like this one, again, under the same constraint, which are not completely blocked, but they contain subsets of sites which are blocked forever. For example, in this picture in which I have a double row which is completely occupied, here on these sites, the constraint is satisfied here in this row. But all the sites of the double occupied row, these two adjacent rows that are occupied, will never be able to update. Okay, so there are these frozen backbones in the configurations, and they will play an important role. So, okay, this is already telling us that we have to be a little bit careful about ergodicity issues because there are several invariant measures, and also that if you want to study relaxation to equilibrium, certainly it will not be uniform on the initial conditions, so we cannot make arguments of the type of worst case analysis. No matter where I start from, I can converge to equilibrium. And if there are experts of interacting particle systems, I wanted also to mention that there are some tools which are often used to study relaxation to equilibrium that go under the name of coercive inequalities, or the sort of type of log Sobolev type inequalities. And here this tool fails. So log Sobolev inequalities diverge, cannot be used for these dynamics due to the presence of these constraints. In fact, these constraints do a thing which is not present in the Ising model. The point is that for this birth and death, for the Ising model, the rate is always strictly positive. It can be small depending on the temperature, on the parameter, and on the configuration, but it's never zero. While here it can be zero, and this breaks everything up. And another general remark, and I think it will be the last one, which is general for all the models, is that, as you might expect, if I vary the parameter Q, I mean, I consider the models, the different models that are obtained by varying this parameter, which enters in the rates, this parameter Q, which corresponds to the equilibrium density of empty sites. The dynamics, the typical time scales of the dynamics of this model will increase, because a smallest density of empty sites implies that typically the constraint will not be satisfied. So I will have to wait longer to be able to relax. And we will see in more precisely how it goes. Okay, I should speed up a little bit, perhaps. So the first question, now, of course, please interrupt me if there is something not clear, or if I speed up too fast. So our question will be to study these time scales and how they do diverge when Q goes to 0 for the different type of constraints. And before answering to that question, because before giving the results, I want to give you a set of results that concern a non-stochastic dynamics, which is very much related to our stochastic dynamics. And in particular, let's focus on this, on the problem of understanding this blocked structure that are present, that can be present in our configurations, depending on the choice of the initial configuration and of the constraints. So in particular, the first natural question could be, if you give me an initial configuration and the model, you fix a model, so a constraint, and you give me an initial configuration. Then the question is, does it contain a blocked cluster? So if I see a configuration with a double row, for example, for the two neighbor model, for the FA to F, I know that it's blocked, but there can be different types of structure. How can I identify them? And are they typically present or not? And the good news is that I don't have to run the stochastic dynamics and look for sites that remain frozen. There is a simple deterministic and discrete time algorithm that, given an initial configuration, allows me to identify the eventual blocked cluster. And it goes as follows. You take your initial configuration, and now in parallel, you look at all sites, and if they are occupied and they have the constraints satisfied, you empty them. If they are empty, you leave them empty. And then you restart again with a new configuration that you have created, and then you iterate and iterate. See, this algorithm, this dynamics is monotone. We are just emptying sites. We are never filling them back. It's monotone, so I will converge to a final configuration. And this final configuration, which I call here eta infinite, so eta was the initial configuration, will either be completely empty, and then nothing else can be emptied by this dynamics, or will contain a cluster, some empty sites, and a cluster of particles which are mutually blocked by the constraints. And the claim, which is not difficult to check, is that the eventual cluster of particles which are present in eta infinity coincides, are in one-to-one correspondence with the cluster of sites of the configuration eta which are blocked under the stochastic dynamics for the same constraint, of course. Okay, I consider my stochastic dynamics. I fix the constraint. I consider this deterministic dynamics with the same constraints. Then the blocked clusters coincide with what remains in the final configuration. That's a good news because this dynamics is much easier to look at because it's deterministic and monotone. And an even better news is that this dynamics has been very much studied in combinatorics and probability in a separate community. So for a long while, the physics community of KCM was not aware about the mathematical community of this studying this algorithm. And this algorithm goes under the name, this dynamics, it goes under the name of Bootstrap percolation, more general U Bootstrap percolation for a general rule U. That's why in my title there was Bootstrap and kinetically constrained models. Okay, so my former question of if I take an initial configuration eta, does it contain typically or not a blocked cluster? Typically here is with respect to when I take eta distributed with the product measure mu, which gives weight q to empty sites and 1 minus q to occupied. So the natural question is that do we have these blocked clusters? Do they percolate, or are they so rare as the double row for the here that certainly, okay, for this double row occupied, for sure in the infinite volume will have 0 probability. But is there something more? Is there more entropy so that the structure are percolate? And the answer is, well, it depends on the constraints. For some constraints, there is a percolation transition for these blocked structures. For others, there is not. And this is a question which is can be completely answered in the framework of Bootstrap percolation, because it's a question just on the blocked clusters. And it had already been investigated. And so since the dynamics is monotone, one can define, so the natural thing is to define a critical density, which depends on the choices of the constraints, which is the smallest density, such that for densities bigger than this critical density, there is no percolation of blocked clusters. The final configuration is completely empty. While for densities, for values of Q, which determine the density of vacant site in the initial configuration, which is smaller, we have percolation of these blocked clusters. So, okay, this is just a definition, but the point is, yes, I'm speeding up too fast, I think, no? Here, the randomness is just at the beginning. Exactly. So I'm making this detour on this deterministic dynamics. Then we will go back to our KCM, which contains randomness both in the beginning and in the evolution. So here is just in the beginning. And the randomness depends on this parameter Q that we fix. And the question is this critical density 0, which means that no matter which is the value of the initial density of empty sites, we always end up having everything empty? Or is it 1, so that no matter which is the initial density, there is blocked clusters? Or is it in between, so we have a percolation transition? As I said, the answer depends on the constraints. Okay, but it's in the next slide. So here, instead of the answer, there is another question, which is the following one, once you want to understand. The next question is, once the critical density is understood, the other question is, how fast do we have to wait in order to empty everything? If we are in the regime in which the initial density is bigger than the critical density, so we know that we will be emptying everything, nothing will remain at the end. But if I'm sitting at the origin and I'm waiting to be emptied, how long do I have to wait? And in particular, how does this time scale, which is this, which I call tau of BP, so the infimum over all the times, the first time at which the origin is emptied by this deterministic dynamics, so this BP stands for Bootstrap percolation, to distinguish it from our stochastic dynamics. How does it behave when we go to the critical parameter? It will diverge. So when the parameter Q is smaller than QC, remember, it means that there is blocked clusters that percolate. So this time can be infinite. So in particular, the mean of this time will be infinite. And so and while above it's finite, so how does it diverge when we approach this critical point? And so any questions? So, and the answers were given in a series of very beautiful papers. Okay, I didn't mention the later ones. So it all started in around 2015 in a series of papers of Bela Bolobash and different collaborators. And that there are other papers that came out this year. These are the papers about for the Bootstrap in 2 dimensions. So this year they had very long and technical papers for the results in higher dimension. But let's stick to Z2. So the answer in Z2 about this critical density is that if you give me a rule, there is a simple geometric criterion where simple means that it requires a number of operations, which is very simple. You can do it easily on a computer or even by hand. If you have a sheet which has squares and not a blank sheet. The number of operations that you have to do is just proportional to the number of sets in your family. So in the case of all the rules that I gave you, it's super easy to control in which class the rules belong. And there are 3 classes of rules. Those that are called supercritical and critical, both do not have a percolation of blocked clusters. So the critical density is always 0. But how are they different is that this infection time for the supercritical model scales as power law with the inverse of this parameter Q, while for the critical model, it scales exponentially when we go to the critical density, which is 0. Instead, for the third class, the subcritical models, there is a critical density which is strictly bigger than 0. Okay, and it's easy to see which are the trivial ones for which QC is 1, and which are those which has a critical density which is really between 0 and 1, so that there is a percolation transition of blocked clusters. So I think, yes.
So in this subcritical case,
yes.
At the critical points.
So the subcritical case is the least understood. So I think I have a slide. So I do have a slide at the end to say that not only for our stochastic dynamics, because I will give you a result in a second, but even for the Bootstrap, it's wide open. Understand there are also, I think that the only results in this setting, besides the results that allows to identify which are the subcritical models and which are those that have QC equal to 1 or QC, there is nothing else. So Ivailo Artalski at the beginning of his thesis had the result on identifying mean, for the percolation, you have two notions usually that usually coincide: the critical density at which percolation cluster occurs, and the critical density for the exponential decay of the clusters. It's not even known if these two coincide. And what is not even known is that we do know, we know how to prove that for some models, this transition is continuous in the sense that at criticality, the probability that the origin belongs to the infinite cluster is 0. And for other models, we know we know how to prove that it's instead discontinuous. So with respect to the percolation transition, there's some richer behavior here. So there are also transitions in Z2 which are discontinuous, but no way to find. Yeah, and that's super open and super interesting. I think you could talk to if you talk to Ivailo once. I don't know if you know, he's super interested on this subject. Okay, so okay. And so now I want to give you, so first of all, the answers for all the zoology of models that I gave you. With respect of the Bootstrap, here is the classification. The East model, the one that was looking, requiring a 0 either on the right or below, is supercritical. So power law behavior and always no blocked cluster. FA1F, the one that is requiring just one empty site, is also supercritical. Instead, Duarte, the one which is looking for two empty sites, but not wanting them on the right, and also this FA2F, they are both critical. And Northeast model, the one which wants exactly two empty sites, one to the right and one below, is subcritical. It's easy to see that in this case, for this problem, it corresponds to oriented percolation, exactly, from the point of view of Bootstrap, this model. So now you might say, okay, but you cheated. You told me that they were on all different universality classes. From the point of view of the clusters, they are not. So these two models are in the same universality class, and these two also. But from the point of view of the stochastic dynamics, we will see, I hope, that they are in different universality classes.
Because so usually in this context, one defines some type of critical exponents, and then actually the universality class is defined by the value of the critical exponents. In this case, for example,
in this case, it's the different for then inside. Okay, I will have something afterwards inside the critical. So okay. So first of all, inside the critical class, what changes? So there are other subclasses which corresponds to the different values of this exponent. This exponent has a meaning. We will see it in a second. But then quite the deceiving thing is that even, and here also you do have an exponent for this power law behavior for these supercritical models. But, and this has not yet been published, I think, but it has been proven by a subset of these people, I think in particular Ballester and Bolobas, that in this exponent here is undecidable. So they connect it to a combinatorial problem in which with a connection with the Turing machine, they show that it's undecidable. Okay, for a single model, to decide in general, it's not possible to give a criterion, but I haven't seen that paper because it has been conjectured for a while and claimed, but not yet. Apparently, so for some single specific rules, for example, for this FA1F, okay, that's easy. Even for the stochastic dynamics, we know how to prove the exponents. But in general, there is not a criterion to prove the exponents. Same here. Okay.
Just another question.
Yeah, but they have a meaning. We will see it, which is their meaning in a second.
I think this tau of this theta exponent or something, I mean, to be kind of related to the exponent that controls the way at which
the control, sorry?
The control the way at which the correlation length approaches infinity at the critical point. Is it related?
Yeah, it's related. In a sense, we see that it's, yeah, completely. It's related even more explicitly to the size of the objects that are able to move. That are typically, in a typical environment, able to move and to allow the relaxation. So it's also correlated to the dynamical length, correlation length. Yes, it's not a static correlation length. Okay, the equilibrium measure is zero, but it's a dynamical correlation length. It is completely related to that. Yeah. Okay, so I'm to my original question. So what we are interested in is the time scales for the stochastic dynamics. So let us go to the case in which the stochasticity is not just in the initial configuration, which is distributed with this product measure, but it's also in these rings of the clocks on the different sides, plus the coin tosses that decide if, in case the constraint is satisfied, to what we update. So now I'm considering the stochastic dynamics, and I call again tau. I call tau 0. Again, this is the first time. Now it's a random time at which the origin is emptied. And now what I'm interested in, okay, one could consider different quantities, but the easiest thing to get into mind is the mean and of this time. And the mean here is over the initial distribution, mu of q, and I'm taking this E written in that form. It means that I'm also taking the mean over the Markov process, okay? And so our question is, how does this time scales diverge when we approach the critical density at which these blocked clusters diverge, and how does it compare with the infection time of the corresponding, meaning with the same constraint, bootstrap dynamics? So a first result, which is easy to determine, and also I think intuitive to believe, is that the deterministic dynamics provides a lower bound for the stochastic dynamics. But in a sense, it's not difficult to believe, because the deterministic dynamics is doing the best that it can to empty everything and to reach the origin. While for the stochastic dynamics, so sequentially, I can empty everything and reach the origin, provided I satisfy the constraints. While for the stochastic dynamics, we are in the regime of small q. Emptying sites has a cost. So I cannot start to empty everything in a sequentially. I have to fill back and do some, I will have to pay some energy barriers in a sense. So, okay, but this lower bound is general, but in general, it doesn't provide the correct behavior. And okay, so I will, so my plan was to,
so we have 10 minutes to the 50.
Okay, okay, and then the questions, yeah.
There is some 10 more minutes to questions.
Perfect. Okay, so no, but stop me when it's time. Yeah. Okay. Okay, so I think I can stick to my plan. So what I wanted to do is to explain for each universality class, the ones that I gave for the bootstrap, which is the behavior for the stochastic dynamics. What I forgot to say is that in the standard slides, up to when I stop talking, I will not tell you which is the criterion which allows you to identify the universality classes once you give them to me. But if you want, I can answer to the question. I have a nice picture afterwards. It's not a difficult criterion, but it's something very geometric. I don't want you to get distracted by this, but it's easy to explain. Okay. Okay, so for the supercritical class, it's the class in which the models that you have to keep in mind is white one perhaps, FA1F. So FA1F. So you need just one empty site to update, and east. You want one empty site, but you look for it either to the right or below. Either to the right or below. And for the bootstrap, the scale, the critical density is 0, and the scaling is power law. In fact, for the bootstrap, you just have to, you're sitting at the origin, and what you want to know is the distance to the nearest empty site. In the case of the east, you have to look for the nearest empty site just in the bottom right quadrant, but it's the same. The scaling is 1 over q to a power which depends on the dimension. While for the stochastic dynamics, we have to refine this critical, this universality class in order to capture the correct behavior. And we identify two subclasses. Again, the criterion to determine them, it's very easy. So once we define these geometric quantities which are needed. And we identify two classes, one that we call the unrooted models, which behaves as power law, as for the bootstrap. And the other one is what we call rooted models, for a reason that I will say in a second. and that scales faster, diverges faster. So the time scales here, so the mean inflection time of the origin, diverges as 1 over q to a power which is log of 1 over q. Okay? And the FA1F model is unrooted, so power law scaling, and the East model instead is rooted, so 1 over q to the log 1 over q scaling. And I want to give you since FA1F and East model are really the key building block to understand all the other dynamics, I want to give you some heuristics about these two models. And I will do this in one dimension because everything is the most important ingredients are already there in one dimension. So the FA1F model, so the constraint requires just one side to be empty in order to make the update. Suppose that at the beginning, I have a single empty site sitting here at X. What I can do is that I can, starting from this empty site, by paying by waiting a time 1 over q, so paying a cost q, I can empty a site nearby. Then when one of these two sites has the clock that rings, typically, because we are in the regime q, which is small, this site will be occupied again. Both of them now have the constraint satisfied, okay? So if in particular is this site which rings first, it means that the original 0 has moved of one step, essentially. So roughly, for this model, what you should have in mind as an image is that the single empty sites can move of one step by creating just one additional empty site. So essentially, they move as a random walk at a rate 1 over q. And in fact, in one dimension, the correct exponent for this stochastic dynamics is 1 over q to the power 3, which is 1 over q because this is the rate of the random walk, and 1 over q squared because it's the distance among equilibrium distance among empty sites that you have to overcome. Okay. This is this mechanism in the case of the 1F, which has what we call an unrooted behavior, so a power law scaling. Instead, for the East model, the mechanism is very different. East model in one dimension is, sorry, I inverted the direction because both conventions are used in the literature. The constraint here for this East is rather west in my slides. So I look for an empty site, but on the left. Sorry for the inconsistency. So suppose I start from a single empty site here at X. Then next, what happens? I can create another new empty site, but I can create it only to the left. So starting from a single vacancy, if I have if I can create at most one additional 0, I can reach only this site. So I wait for a time 1 over q, I can reach this site because on the left, the constraint is satisfied. But now what I can do is I cannot fill this site because its constraint is not satisfied. So the only thing that can happen is that this site is occupied again. If instead I have I can wait for a time 1 over q squared. So I have I can wait to create 2 additional empty sites. What I can do is I can empty this site and this one. And now this site can be occupied because the constraint is satisfied. So I can also reach this configuration. But see, I can also this other configuration, reach it with 2 additional empty sites because now I have, this was the original one. I had created 2 of them. I have taken away this empty site thanks to this constraint, and now I can create an additional empty site here. Okay, so see, if I have at my disposal 2 empty sites, starting from X, I can go up to X plus 3, putting an empty site. And now I claim, and it's a nice combinatorial argument, a nice combinatorial exercise, that if you have in your pocket n additional zeros that you can put simultaneously, and you don't cheat, so you follow the constraint of the model, you can reach a configuration which has a rightmost 0 at 2 to the power n minus 1, where n is the number of additional zeros that you are willing to pay. And all the other configurations that you reach have the zeros which are to the left. So this is the farther distance that you can reach to the right with this satisfying this constraint. What does it mean from the point of view of our stochastic dynamics? So it means that, so you see there's this 2 to the power n. So in equilibrium, the first zero to the right, to the left of the origin is a distance 1 over q. Okay, I'm sitting at the origin here, and I'm waiting. Waiting for what? Waiting, and I'm filled, suppose. So I wait that the first empty site to the left is able to send me an empty site in order to allow my update. How long does it take? If this distance is 1 over q, I know that, so this is what corresponded before to the 2 to the power n. It means that to overcome that distance, I have to create log of 2 to the power n additional simultaneous empty sites. So that's why I have to pay a price, which is the price of creating a single empty site to a power which is log of q. So this constraint is creating a very different behavior. It creates some logarithmic energy barriers that I have to overcome, and that justify this divergence, this different divergence. Okay, here there were some further results about, okay, one can also find the exact constant in the scaling by taking into account the different ways to overcome this barrier, but it's not the main thing that I wanted to say here. What I wanted to make you notice is that while for the bootstrap dynamics with this is constraint, the scaling is just 1 over q to the power 1 over d, where d is the spatial dimension. It's just the distance to the nearest zero. Here, in any dimension, it will always be or the form 1 over q to the power log of q. Okay, so now that I have these two building blocks, I can explain you about supercritical model, these two classes, unrooted and rooted models. So essentially, you have to think about them as the following. The unrooted models behave like FA1F, with the difference that the roots can be much more complicated. And essentially what happens is that the role of the single empty sites, which those that make this random walk, for this supercritical unrooted is played by some droplets, large but finite, that can move back and forth, can create a new droplet, and then the other one is filled, etc., etc. Instead, the rooted models are those for which the motion is like for the east model. So rooted because there is a sort of cone of direction in which we can move, but I cannot move wherever. So it's like if I start with an empty site for the east model, from a single empty site, I can empty everything here, I can empty everything here, and so on, but I cannot empty whatever. Okay, depends if the constraints are east or west. And so this gives rise to this logarithmic scaling. So logarithmic in what? In the distance to the droplet, but these droplets are finite, so they will have a distance to the origin, which is just 1 over q to the power the size of these droplets. Now, for the critical models, I'm not sure I will say something more on Bootstrap, or yes, perhaps yes, because it's interesting. This critical model, as I said, again, for example, the two neighbor model, the FA2F model, for the Bootstrap, I told you that, I told you that the critical density is 0, so there is no blocked clusters, and the time case is exponential in 1 over q, in 1 over q to a power, which for this model is just 1. And which is the reason of this scaling is the following. For FA2F model, if you start with a region which is empty, no matter how big it is, it will not be able to move to create other empty sites. You see, you start from a completely empty region, ups.
No.
No, because this is different. Okay. Unless, yeah, it's okay, I think, no? Yeah.
But this one is actually going to expand.
Okay, it will appear in a second. So from, yeah, for this rule, it's already the next slide. Okay, I cannot expand because you see this region of empty sites is trapped by the presence of all these filled sites around. I cannot expand it. But the point is that it's sufficient to add for this FA2F rule a single empty site, this green one they added here, in order to be able to sequentially empty the next column. Okay, so I won't add much more, But I want to say is that for these critical models, it's not possible to identify finite droplets that are able by themselves to move. But if I take them sufficiently large, in particular here of the size 1/q log 1/q, typically they will find, typically in a typical environment, they will find at least one empty site around, which will make them able to move. So essentially, you should think about critical models as being renormalized models of the type East and FA1F, but now where renormalized means on a size which itself depends on Q. And because now I want to jump a bit, but it comes to your question. So the size of this typical region that will have to move. So for the FA2F model, it's of the form 1/q with log correction, hence a scaling which is q to the power of this, so q exponential of 1/q. Let me forget about log corrections. But in general, for generic rules, in order to move these big droplets, I will need more than one single empty site. Suppose I need two of them. So these two will be what appears in the exponent. So this is what is called the difficulty of the constraints. The difficulty is the minimal number of additional external empty sites that I have to add in order to allow the motion. And okay, the point is that again, I mean, I want to want to enter in the details, but again, it's like what happened in the supercritical case. Again, for the stochastic dynamics, what I wrote before is for the deterministic bootstrap dynamics. For the stochastic ones, again, we have to refine the universality classes in order to catch the correct behavior. What changes here is the exponent in this exponential. So for a class of model, which we call a subclass of models that we call finitely critical, this exponent is the same as for the bootstrap. For another class of model, this exponent is double the one of the bootstrap. And the reason is that for those that have the same exponent, the motion of the droplets, these big droplets with the size which depends on Q, is similar to the one of FA1F. And for the others, like the Duarte model, this motion is instead East-like. So it will require overcoming logarithmic energy barrier. Now the logarithm is in the distance to the next empty droplet, and so itself it will bring a 1/q in the exponents, hence the doubling of the exponents. I went a bit fast on that, but so this is the Duarte model, and so it's typical droplets that can move these columns, and in order to move them, they will have to overcome a distance which is which diverges as exponential 1/q, hence this cost. Okay, this was something about, so I can tell you if you want to know more about mathematics. So this is just the heuristics, but mathematically, what do we use as tools? So you feel free to ask in the questions. Yeah.
The droplets are actually growing.
Yeah, they have a size which depends on Q, and yeah, and not only they are growing, but you don't have to think about them as being some rigid objects. They can deform themselves during the dynamics, so otherwise they won't be able to move. They can deform them, disappear. But essentially, okay, the main tools that we use are renormalization to go on the scale of the droplets, Poincaré inequalities. So it means that we are studying a heating time, the inflection time of the origin. We connect the heating time to a Dirichlet problem. So they're studying the eigenvalues of the generator of the Markov process. And then we establish Poincaré inequalities at the level of the motion inside these droplets and at the level of the motion of these droplets. And that's how we derive things. And then we use some canonical path arguments. This is a bit more technical to make these motions, to make the comparison of different, to go from one Dirichlet form, these forms that of which we are going to evaluate the spectrum, to another one. And just one thing that I wanted to say is that we will also have to do some algorithmic construction of the bottlenecks of the dynamics, which will allow us to say, okay, so we are not slowest then because we can relax like that, but we are also at least as low as because of the presence of a bottleneck. And great, that's all, because I already said that subcritical essential we know nothing. So thanks for your attention.
Thanks a lot for the very inspiring talk. And so there have been many questions, I guess, but if there are some urgent ones, we can ask now. Otherwise, we can move it to the break. And I invite you to ask so many questions too. Yeah.
Are there questions on Zoom?
So no questions from the audience?
We're waiting to see if the online people have
Okay.
questions.
Well, in the rules, you check if you have empty vertices, but you can check if the vertices are also filled. No?
Yeah,
In the rules.
but
Does it change a little?
I mean, the rules are always monotone in the sense that once you have verified that it's satisfied for one of the, because one of the update sets is empty, you don't have to verify anything else. It won't
You
change.
might also check if some vertices are filled.
Other outside. You mean make a mixture of constraints requiring some field sites? Not sure that we could extend the techniques in that case. If we mix some constraint that requires being filled and some constraints being empty, not sure.
Any other question? Thank you so much.
Thank you.